All right, we can start off. So for today's session, I hope I'm audible. If I'm not audible, please let me know. For today's session, I just wanted to go over the tool stack that we have in our environment and just a brief introduction on some of the tools, Hadoop tool stack, and how at the architecture level or at high level how things work, and basically go through each tool stack and see a couple of examples, and maybe we can wrap up for today. I don't want to hold you guys for too long. So I hope I'm still audible for everyone.
Yeah,
Yeah.
yes, you are.
Okay. So today
Yes.
we
Yep.
will be looking at mostly these tool stack. I just want to go over the overview. Most of you might know most of the tool stack, what it does and what it doesn't do. But I would like to still go through, since it's the introduction part of it, I would like to go through the introduction of each tool stack for the people who don't know. Um, so let's kick this off with thank you everyone once again for joining. And all right. So first of all, why even do I know a lot of you people are from EDW background and you have a lot of experience on the data warehousing concepts, and you've been doing a lot of these things from a long time. That being said, um, as we know, in late 20s, a lot of because of internet boom, there was a lot of change in how the data was getting generated. It was no longer structured data, so everything started getting complex, and there started being like this boom of data change, or how the internet brought in all kinds of data all across the world. So the sheer volume of data, of how data came into the data centers, increased exponentially. To address this problem, we none of like all the startups or people like you and me couldn't afford for like high-end data processing systems like SQL Server or Oracle servers. They and mainframe servers, they are expensive, and they had one problem where you had to take the data to the data centers, right? Right. So you had a huge set of machines or supercomputers laying around, or the servers, where you stored the data and did the processing on the server, which was really expensive. So to address that is where big data or the Hadoop um, came into picture to address this sheer problem of volume, variety, and velocity. What it basically means is there is so much volume of data that gets generated every single second, and there is all kinds of data. So be it text, audio, images, um, videos, and ev- everything that we could possibly imagine. And the speed at which these data get generated i- is unimaginable. So to address that is when basically this Hadoop project came into picture. Basically, Hadoop was invented or designed to address the problem of high-end computing costs, where to solve all these data related problems with lower, cheap hardware, or um, cheap, reliable systems where everyone can afford. So even a startup can basically hook up like uh, 10 laptops together and stand up a Hadoop cluster and process like this huge volumes of data, right, using the commodity hardware. So that's how Hadoop's birth came into picture, to solve all this distributed um, uh, system challenges. The um, mm, Hadoop was mainly designed to handle this distributed data problems with keeping in mind the fault tolerance and the cost effectiveness and so on. The guy called Doug Cutting in 2005 started working on it. That he basically this project came into picture to address the Notch search engine project, where Notch is basically a web crawler at Yahoo, and Yahoo actually funded this project, and that's how Hadoop kicked off around 2005. Since then, Hadoop has grown to be like this a huge ecosystem of tool stack. Mostly Apache open source community actually owns a lot of these tool stacks, and they develop, and there is like companies like Cloudera and Hortonworks. Now Cloudera bought Hortonworks. All these people, they take these open source and they commercialize it, and um, there is a lot of other Hadoop related tool stack like HBase, which deals with like columnar data stores, which uses like the semi-structured data or object mm, like a data that is object centric, right? So HBase, Hive, Pig, and most of these tools you might have used, and some of the tools we don't really use at our environment today. There's a reason for it because we there is no direct, like for example Scoop. We even though a lot of our data come through from EDW, we can actually use Scoop to get the data out of EDW and dump it onto our cluster, and then move ahead. It's like a direct connect. It scoops data out of traditional RDBMS data stores, but we don't do that because there is no direct connect between our AWS cloud to our BCBSM network. So there is this security constraint that we have. That's the reason we don't use Scoop. And as far as Hive and Impala, we use that a lot. Um, and I will be going over each of these, some of these tool stack. I won't be going through the tool stack that we don't really use, like Pig scripts. I don't think anybody uses Pig anymore as much. They used to use it before. And Flume as well. Flume, we don't use it. But I will just briefly go over that just just to understand how things work. So that being said, Hadoop's architecture. Hadoop,
Okay, sorry to interrupt you. Is
yeah,
it getting recorded like?
yeah, it is. It is being recorded. I
Okay.
will send out the recording once
Okay.
we're done. Yeah. Yeah. All right. So Hadoop's architecture. So we need to know one thing. Hadoop is not a replacement for ADW or a traditional RDBMS data stores. You cannot compare what you have, like this hundreds of thousands of dollars worth uh, um, this production hardware of your SQL Server with Hadoop. It's not the same thing. It's not apples to apple comparison. Hadoop is like a cheap replacement for your data processing needs. So that being said, in our environment, there is this weird um, understanding with everyone that SQL Server can do this, Hadoop cannot do this. There are things that Hadoop cannot do, and there are things that Hadoop does better than SQL Server and cheaper than SQL Server. So there is a lot of architectural and design pattern specific differences between these two. So we cannot directly compare them. Like some of the things that we want, if I want to talk about, is updates. So Hadoop was not built to built like update file system. It's more of like a read only or append only file system. So Hadoop is best suited for reads. Writes are actually slow, but reads are faster in Hadoop. Uh, but there is no direct update features like what you have on SQL Server side. So it's called as a update on append only file system. So where you get the data every day and keep dumping it onto a distributed file system, and then do your analysis and build your so-called data marts or other layers that we work on today. Unfortunately, we do have this pattern of, oh, I need the SE type 2. It's a business requirement. I completely understand from where we are coming from. At the same time, we are trying to ask a system that really was not built for updates to do updates. So that's where we are doing today. If you see a lot of the workflows, we do insert override. Insert override is basically truncate and reload of the entire table to just to mimic the feature of update. So that's what we do on our Parquet storage file system. I'll go over the storage file systems once I'm talking through Hive. But just so you know, Hadoop was not built for updates. That being said, the concept, the core concept of Hadoop was there is this, let's say, distributed set of computers or nodes, you may call it, where you have a master or a tracker node that keeps tracks of the jobs submitted, and you have the data nodes where the data resides in the cluster. Let's go to the picture. So. Um, Basically, you have set of data nodes where you have all the data stored, where the data is replicated across the cluster based on your replication factor settings. So think of the data stored on Hadoop is mostly files. So everything is files. So it's like blob of data replicated across the nodes, right? So it's not like a traditional table or database, although it looks like it is mimicking the traditional RDBMS structure, but it's underneath. If you basically get away from that UI and everything. So underneath, everything is working based on the files. So the files get replicated across the data nodes, and when a client submits a read or write to the system, it goes through the name node, where name node knows where it keeps track of where the data resides, and data nodes respond back. Okay, this blob, let's say file XYZ, resides on one of the data nodes, and the data is replicated. Let's say usually we keep replication factor of 2 or 3, so that the data, at least we have one extra copy. If one of the node goes down, still it's fault tolerant. So the system is not really down. So the other system is still responding to your requests, even though one system goes down. That's how these nodes work together to solve your problem. Basically, the concept was to bring, it was not like in traditional systems what mainframe or SQL Server does, where you take the data to the data center where all these heavy machines do the computing, and then you get the data out. But in this case, in Hadoop's case, that was not the case. To address the problem of data serialization across the network, what they did was basically you stored the data on data nodes, and the computing, you take the computing to the data. Basically, the computing happens on the nodes. When you submit a job like a Spark job, basically the Spark also does the master-slave architecture, where when you submit a job, there is a master or a master key or a job tracker that keeps track. Uh, let's go back to name node. So here name node stores all the metadata of files. like the directory and where the files reside, and name node knows. So that's where recently we have had, if you remember, we have had problems. I don't know how many of you were involved. If you were involved in one of the IE projects, you would have known that we have had downtimes recently. That was because there was a problem called like too many small files. So when we do an ingestion of a data set, we make sure that you do a repartition. At least on Spark, you do a repartition and you split the files based on uh, uh, the uh, oh, I'm forgetting. Based on your block size, you split the files based on the block size, and then you write the files over to HDFS, right? So that previously what people were doing is basically doing this right without keeping in mind how many files they are writing to HDFS. So like for example, you have 1 gigs of data that you're writing to HDFS, and let's say for example your block size is 256 MB. Um, Ideally, your file should be split into, like, Hadoop splits into 4 chunks, right? You have 4 chunks divided, 1024 divided by 256 MB, right? So that's basically your calculation that you need to do in Spark today. That's what we do when we do the repartition based on the size of the incoming file. Why is that important? So if you don't really maintain that block size, uh, name node there is a really name node has to work harder to find that uh, number of files. Like I said, Hadoop deals with files, so there will be thousands of files to deal with. Now, for example, you need to find, let's say, in a table that has 1 GB worth of data, instead of let's say you're trying to find a record which is supposed to be in, like, if we followed the block size, it was supposed to be in 4 files, right? So 1 GB, 4 files. But since we were not following that pattern, we were not writing in the block size, so all these writes were writing all these files to like thousands of small files, like in KBs. So what happens when you issue a query through Hive to Hadoop or the name node? Now name node has to scan through these thousands of files, which becomes a problem, because opening and closing of file headers is an expensive operation. So to avoid that is where you have to maintain the block size. Um, that's where we had a problem of block size problem, and we introduced, or we made it mandatory for everyone who's working on a dev team to actually keep this in mind while writing files to HDFS. So uh, that is name node, where name node handles, it keeps track of all this information. And and then you have this data node where all your files are stored, where each file, data node basically splits based on the block size. Um, let's say you write a 1 GB file directly to HDFS. How does data node underneath it splits and keep tracks of which block resides on which data node. So you might have 10 data nodes. The data might be replicated across. So now data node knows, name node knows uh, where the block resides, and it's data node's responsibility to let the name node know which block it has, right, for a given file. So that's how the MapReduce concept works, where this data is replicated, and name node and data nodes and job tracker works together to complete your task. Basically, when this is how a MapReduce job is submitted. And remember, so ideally, a lot of, like, if you know Impala, we know that Impala is faster than Hive. That the reason basically is Impala doesn't do MapReduce. Hive does MapReduce. MapReduce is slow, very slow compared to compared to like in-memory processing, which Spark and Impala and all these systems do. We will go through that in some time to understand how what is the primary difference between like this MapReduce concept and how the in-memory concept differs and how the speed increases with both the systems. So just to understand Hadoop's architecture, like when you submit a job, any kind of job, like even a simple Hive query, Hive actually invokes a MapReduce job on the backend. So when the job is submitted, the job tracker keep tracks of the job, and it goes through this MapReduce mapping mapper uh, uh, mapper stages and then the reduce stages. So basically it goes through the data nodes, gets the splits of data that's stored on your distributed file system on HDFS, and your mappers basically scans through the file and tries to identify each of the data that you might need and try to aggregate. Maybe you are doing a max problem or finding a particular record through a table. So all of those go through the map and then reduce until that desired result is achieved, and that is job tracker basically keeps track of which node is performing which action. So in Spark, you might see something called, if you go through Spark UI, when you submit a job, you will see there is something called stages of tasks happening. So each task is like a minute problem that each node performs individually, and then it finishes that task and responds back saying, okay, this task is done. And basically the job tracker keeps assigning the jobs to all these nodes, and the jobs complete, and the reduce phase goes through, and the problem is completed once the reduce phase is done, and then the output is given back. So that's kind of like at the high level. I didn't want to get into the details of how the data is moved across and how important it is for you to consider shuffling and everything. We can talk through that during the best practices of Spark. Uh, why you should avoid shuffling and how to avoid shuffling and such kind of things. So as of right now, any questions?
How is that thousands of files getting generated? You said files are getting generated in
Hmm.
KB size.
Yeah,
So how is that issue got resolved? Is that due to blockage only?
yeah, good question. So what we did, and so out of the box, be it in Spark or in like we can use your shell scripts. Initially, we were doing shell scripts, I believe, and then we transitioned progressively to changing the coding pattern, right? So each phase we improved upon one or the other things. So the small file problem is basically when you don't specify the number of partitions or number of splits of the files while writing the data to HDFS. So I will go through. There are two concepts in Hive, right? Two types of tables, which is external and internal. I'll go through that in a minute. So when you do external table, you are actually taking responsibility of, you're saying, okay, Hive, you don't manage all this life cycle of managing the data. I will manage the life cycle of data myself. So I will make sure how the data is written, how the data is aggregated, how the data is partitioned, and everything, right? So that's what we do. A lot of our workflows, we do a lot of external tables. The reason being, it was basically a architecture decision where somehow somebody drops by mistake a table, we don't lose that data. Basically, in external tables, if you drop a table, you don't lose the underlying files. The files are still intact. But if it's a managed table, if you do a drop on the table, the files are lost. That's the reason we did that, going through the external phase. So in that case, while you are writing data to the table, so you should make sure that you are actually writing in blocks. So in our environment, the block size is 126 MB. That's the block size, but you can write greater than the block size, but not too big of a file too. So there is you need to maintain both. So you cannot write smaller files, and you cannot write bigger, too large of a file, right? So you cannot have like 1 gig of file laying on the on HDFS all, or like 5 gigs of files. Even that becomes a toll, because now when Hadoop opens that file, it has to, while scanning through those data, like for example, if you take Spark, it's actually doing all the computation in memory. At least Hive or MapReduce does a read write on the disk, so it's not as much memory intensive compared to this Spark or Impala and all these data sets. So you will run into, if you have like bigger table scans or bigger joins where table is not particularly properly partitioned, and you're just issuing this huge queries, you will start seeing like this memory spilling problem. So we have a limitation on how much memory each query can use. We have had problems where COE team or the other team, CMO, data scientist team, they started, writing this huge bunch of queries, which was not really properly optimized, which was bringing the cluster down. So we put in like controls on how much a query can consume in terms of memory when you issue the problem to the server. So that restrictions are in place, but still there are workarounds on how you can write a efficient query, right? So to answer your question, sorry I took a long route, but to answer your question, it depends on what kind of table you are creating and how you are writing data to those tables, right? So if you are managing the data lifecycle, then you have to make sure to write all these files in a given partition block size. So which we were not following, and we were writing all the data in KBs, all the files were getting written in KBs. So that basically become a huge problem for name node to scan through all those KBs of files to complete a query. So basically name node becomes very busy, and the cluster goes down. So we should avoid using this like too many small files. Any more questions? All right. Okay. So let's go ahead. Next, I would like to talk about Hive, which is our querying, SQL-like querying language on Hadoop. Basically, it does a scan through of files on HDFS. HDFS is nothing but Hadoop distributed file system, where you store all your files. When you write a data or a file to the table, it's stored on HDFS. Even though it's stored on physical file system, Hadoop manages using the Hadoop distributed file system. That's how the blocks are split, how and where the blocks reside, and that's how the data nodes now using Hadoop's distributed file system.